give it another 2 minutes, I guess. All right, let's get started. So, continuing from the last week, which we kind of motivated the geometric deep learning a little bit. So today we're gonna look more into geometric deep learning, especially like one series of work that mainly captures the translation rotation invariance. So we're gonna learn a little bit about the overall landscapes about geometric deep learning and some mathematical concepts such as group and representations. And we're going to mainly focus on invariance today, but the next week we're going to talk more about the equivariance. All right, so before we start, a quick announcement is so we're having a little bit issue with setting up the autograder for PSET3. So PSET3 will be released next Monday, and the due date will also be delayed for 3 days. So it will be after a Friday. Due after a Friday, so you'll be able to go to the office solver and talk to TA before the due dates this time. So if you don't see the homework out today, don't worry. Like we will postpone both the release date and the deadline for the due date for PSET3. And PSET3 is mostly about some basic graph neural network and geometric like equivariance and invariance operations that we talk about in this lecture and next lecture. So yeah, it will basically we will cover the material. The problem we give out will be something relevant to what we cover in the lecture. All right, so to recap, last time we defined a geometric graph, which is a special type of graphs. So consider like graph as a more general version of geometric graphs, but geometric graph is more special, and therefore particular types of features or attributes associated to geometric graph will undergo different limitations in physical world, and therefore, even though it's a specific type of graph, a lot of more attention can be paid into designing algorithms that learn over these geometric graphs. Particularly, what differentiates geometric graph from a normal graph is that the notion of geometry, which can be thought of as attributes that are derived from a 3D coordinate system. So in the normal graph, we only have adjacency matrix, sometimes has some edge features, or sometimes just adjacency matrix. And we have node features, and we have always treating them as just a scalar feature, so you can do any operation on the scalar features and still get a scalar output. Alternatively, in the geometric graph, we would divide our node features into 3 types of features. The scalar feature is the same, so it can be high dimensional, but they will be treated as if they are like scalars. And there will be coordinates, which usually denoted by x or sometimes p. And then there's a set of geometric features which are the kind of the derivative or the outcome of the things that are operations that are related to coordinate. For example, velocity or acceleration or forces, or even higher order operators that are related to the spatial features of each node in the graph will becomes the geometric features. And to embed this kind of graph, we can of course use normal deep learning, and we can try to add in the permutation invariance with graph neural networks. But still, because we know that there are particular types of new equivariance and invariance that we want to capture that are unique to the geometric features, we may think about different way of designing neural networks that basically apply special inductive bias, such that we can learn similar rules with fewer data. So a lot of the real-world structures, actually not just structures, but a lot of the relational data are geometric graphs. Last time we mentioned a little bit, but here are more examples. For example, from small molecules to a lot of different polymers like proteins and DNAs, and a lot of these inorganic crystals or material science. You have this small unit, repetitive unit with kind of periodicity. However, overall, when you look at this whole system, they're strongly connected by rules, like physical rules, and therefore their geometry also matters. In the real world, other than biology and molecule design, there are also different other kind of geometric graphs that people try to apply geometric deep learning for, especially 3D point clouds. All of the graphic stuff, you can imagine, basically share very similar creatures as the chemical and protein molecules. For example, transportations can also be considered a geometric graph, even though it might be on the 3D, on the 2D space where you have this roads and transportation system as the grids, and you can consider that entities over this grid actually have physical meaning, their positions and distance actually matters. So this can be dealt with as treating it as a geometric graph. For computer vision and robotics, of course, robotics related. We're dealing with, again, real-world physics. So a lot of the robotics operation, like rotations, are also constrained by this physical constraints. We're in a 3D space where you can't just go anywhere as you want. And in computer vision, actually not just the 3D computer vision, but also 2D computer vision, you can treat basically 2D pictures as a geometric graph as well, right? Because you could potentially move the object in the 2D space as well, and you would also expect some invariance and equivariance, even if it's a 2D graph. So it's not something that's specific to 3D. All right, so why do we need, where can we apply geometric deep learning or geometric graph neural networks? So there are definitely a lot of different potentials for this kind of architectures. We can use it, of course, for making better predictors, which are kind of like supervised learning models. A lot of the properties that we're predicting, for example, like binding affinity, right, or anything related to kind of the biophysical interactions of the atoms and their properties, they share these geometric symmetries, right? If it's the same molecule, if you translate it or you rotate it, it should be still, again, the same molecule, and their functions should not change. So this is a kind of invariance to certain types of geometric operators. And more importantly, especially this is kind of emerging domain in the past 1 to 2 years, we're getting better tools in terms of generative model over structures, particularly with diffusion and full matching, which we'll talk a lot in the later part of the semesters. We found that these equivariant or geometric aware deep learning models could significantly improve the consistency of these generative models, making better awareness of these 3D space information. We'll be able to also build very strong 3D generative models using these networks as the backbones in the diffusion or flow matching. So more importantly, or this is not more important, but naturally, extending beyond just generative models, you can consider basically simulating the real physics with machine learning as well. right? So, but I think these two type of applications share some similarities. For example, you could solving both of them using kind of some notion of ODE or PDEs. But what's important is basically both the model, you need the architecture or a function that encode the current state or current 3D geometric information and try to predict the future stage of the 3D geometric information. So there is kind of the continuity in both space and time. And therefore, the geometric GNN can greatly save our computation or the data that's needed to learn corresponding operator in the 3D space. So as we talked about last time, well, not all graphs are geometric graphs. And when we talk about geometric deep learnings, we particularly want to leverage certain symmetries that we know that exist in the physical space. And we want to respect these constraints by injecting the similar inductive bias to our function, the function which is characterized by a deep neural networks. Particularly, this is a recap. There are two types of transformations that are important and that we usually consider. Is the translation operation, where if some of you are not here, translation means kind of directly adding a 3D coordinate, kind of change of coordinate into your current systems, and basically you can consider moving the whole system or your whole representations with respect to some direction that's characterized by, for example, a 3D vector. And the other type of operations are rotations, which usually can be characterized with some, again, like matrix multiplication with rotation matrix. And we'll expect that a lot of the features, especially geometric attributes related to rotations, will be equivariant to this transformation. Means that if you rotate the coordinate system, all of the vector features will be rotated in a similar angle in a similar way. So this is kind of a high-level understanding of equivariance. And this is the example I showed last time where you could consider this invariance and equivariance as properties or physical constraints that in the real world, and it's describing like how particular attributes of the system will change when you apply this transformation. It's not about like what your model can model, right? It doesn't mean like if you have some changes that are not translation rotation, then like your model is not learning about these changes. It's only about talking about a certain type of physical constraints about the input space and the function. So this is not about model yet, but we can consider like these are the natural rules that exist in nature, such that if you perturb the system this way, right, then this corresponding attribute will change in this way, or it will not change, which is invariance. It's about the kind of the fundamental rules that governs the data. But because of the existence of these rules, we try to design functions or operators that kind of mimics this like actual rules in physics. So if your model have that inductive bias in it already, even if you have a perturbed version of the data, you will still be able to converging to the correct function also faster, because the model doesn't need to tell the difference between something that shouldn't be different, because your model have that inductive bias already. So in a high level, we could think of geometric deep learnings being coming up with neural architectures that can deal with different types of features, and it handles different features separately, such that the needed invariance and equivariance is preserved after the function is applied to these features, right? Particularly, we want the scalar features to be invariant to these transformations, and we want the vector features to be mostly equivariant if these vector features are geometric attributes. You could have like other high dimensional features, right? But there's a distinction between scalar features which are irrelevant to or insensitive to these geometric operations because they're always held invariant. And there are certain high dimensional features that have this geometric property behind, so that it should be updated in the equivariant manner. And we will define equivariant mathematically in the later part of the class as well. But in the high level, we can see that basically if certain operation is applied to the raw system, the operation will be applied to, the function that you learn over the original input, the original input features, including scalar feature and vector features. Thinking about that will embed your features into some manifold, right? And the equivariance here in the high level means that if you apply the function first and then apply the operators on this manifold, it will be equivalent to applying the operators on your input space and then apply the function that maps to this manifold. So, so this is kind of a high-level demonstration of equivariance. Any questions so far? All right, so so if you recall about normal message passing, right? It's basically about learning a function that propagate information from the nodes to its neighborhoods, and then the aggregation of these informations or message that we note. So now that we have a special type of information in the node, which we call kind of the positions, so now the geometric message passing is really not very different from the normal message passing. The only difference is that when we design this message function and aggregation function, we want to handle the geometric information more carefully. So, so basically, we want these this edge or the message contain the geometric information, and we want to make sure that after this phi transformation and this and this aggregation, the key properties that propagate to the next node undergoing operations that preserve some equivariance or invariance. So the whole kind of geometric deep learning or geometric graph neural networks where message passing is involved is kind of the study where we try to come up with different functions, that we design different functions for computing these messages over the scalar and vector features, as well as how we aggregate those information to get the new scalar and vector features. And positions can be considered like one part of the features here as well. All right, so before we dive into the algorithm, actually just try to model the 3D atomic system is a non-trivial task, right? Because you think about it, you start from like random molecules and suddenly like you say that we have a model for it. So it's actually a non-trivial path, and there are a lot of efforts of just putting into how we like process the data and how we come up with models to try to model these type of data, right? So here is one example of kind of a common pipeline that we will see when we use like geometric deep learnings in atomic system and handling like computational biology and computational chemistry problems, right? So we start with these databases of geometric graphs again, right? In this databases, we have the entities that we need, which are the coordinates, the vector features, and the scalar features. And sometimes people also treat them as point cloud, because if you don't have edges at all, right? If you just look at the nodes in the graph themselves, is kind of like the isolated points, but with the sets of points, they preserve some information about geometry. So even without the edge, you could represent a like kind of an object with geometry information, which is we call point cloud. And a lot of the, I mean like protein molecules, if you only look at the atoms, right, they're actually point clouds, if you don't consider like bonds or interactions between them. So so you can actually define all different type of graphs over these small molecules, where in the geometric graph, we sometimes consider building edges based on their geometric information. But you know that in small molecule, for example, you have chemical bonds, which are explicit defined graphs, right? But that edge can have a different information, carry different information than the geometric edges in the geometric graphs, which could be like a distance between two atoms, right? So after we have this raw data of point clouds, maybe some like chemical bonds, we then try to turn this representation into a geometric graph. So the difference here, we have this A matrices here, which is the adjacency matrix, which preserves the proximity of the nodes based on their geometry data. So this is slightly different than the graph learning that we dealt with previously, where the relationship or adjacency matrix is already given or is already defined by the data providers. So in the geometric graph, you may not have this edge defined previously, and you could, in this input representation stage, we may think about different pre-processing steps to create the graph, basically define the neighborhood structure from these pre-processing steps. So after having this geometric graph, we're then using some embedding blocks, like treating that different part of these features as kind of some quantity that related to biophysics, or chemical properties. For example, the atom number or atom type is naturally one type of scalar features, right? And you can consider other like periodicities or some basis functions as a way of characterizing, or as kind of a feature related to the geometric attributes. And we want to build these embedding blocks, which are basically the message computation network that try to make use of these geometric and scalar features and turn them into some intermediate representations or intermediate features that corresponds to some of these biophysics that we think are important. And then after getting these messages or latent representations, you can pass them into interaction blocks, which are basically the key part of the most important part of geometric deep learning, where we define the message and try to do message passing along the graph. And before and after that interaction blocks, we try to make sure that this latent representation has certain correspondence with our input graph, so that the intermediate change will preserve the relationship between the input graph and these representations, such that in a way that it will keep the invariance and equivariance. And finally, we can have a transformation block that transform the hidden representation into the final predictions, which are the actual properties we want to predict. And those properties are where the actual invariance and equivariance come from, which is the data. Because in your data, all of this property, for example, energy, and will naturally be invariant to translation rotations in the input graphs. And similarly, the coordinates and forces will be equivariant to translation rotations in the input graph. So you can see that this whole pipeline is, again, like you can consider this as one special type of machine learning pipeline. You could basically replace any of the block in the middle with like normal deep learning architectures, and you can still train a model to learn from the input graph and these functions, right? It doesn't mean that you cannot learn it if you don't use geometric deep learning. Of course you can, and that's actually what the AlphaFold 3 did in the most recent version. They actually removed a lot of this complex inductive bias in the middle, but as long as you have tons of data between your input graph and the output, your data preserves that equivariance already. So like you could have a very flexible black box deep learning model, and you just blindly learn this function mapping, right? That's still possible. But what I'm saying is, if we design these interaction blocks with more careful operations, we need fewer data to learn this function, because kind of the degree of freedom that we need to learn is smaller, because there's certain freedom that is already restricted by the model itself. So your model can just need to focus on the residual part that try to link these symmetries to the actual functions. Okay, so we talk about this input representation a little bit. So now I'm giving a little bit more example of how you might go about building a graph from the point cloud. And this is not the only way of doing it. You could, of course, consider other types of relationship, but these are the most relevant way of building the graph. And note that the graph information here is not, it's not the same as kind of the geometry that the network, the inductive bias of the network is capturing. This is rather just defining the local neighborhood which will engage in message passing, right? So basically, this should not impact whether your architecture is equivariant or invariant. It just define a different graph such that you can do message passing over the graph. And if your architecture is invariant or equivariant, it should be insensitive to how we define this graph. All right. So that's why sometimes you don't need a graph neural networks for this task, right? There's also like SC3 transformers and IPA, which we'll talk about in the AlphaFold section. Sometimes you just don't need to build a sparse graph, and you could connect everything and get a complete graph where you take all the information in your system into consideration and apply geometric deep learning over them. But this is just a case where this is just representing the case where you do want to prune that connectivity a little bit. So you want to be kind of more focusing on some local interactions, and therefore you could build this graph with some geometric, with some thresholding techniques or some rules that you need to follow on this unconnected 3D point cloud. So what most common way of building the edges is through this cutoff graph function, where basically you just take k nearest neighbor based on their geometric distance. So you will have a graph, like an edges built between points that are closest in the neighborhood space. This is the most naive way, but very effective way of constructing kind of a graph information. And you can also have some notion of like long-range connection, where you sometimes what people do is you first build a k nearest neighbor graph, and you randomly kind of connect some pairs in the graph, so where you can randomly add in some long-range connections. Questions?
Do people ever try to kind of predict what the most likely long-range connections are, or is it completely random in the models that you've seen?
I think this is a pre-processing step usually. Like you fix it and you model it. The graph architecture don't usually change. The topology don't usually change. Questions?
Do people in this model like coarse grain long-range interactions? Like I know
I see.
The motivation for asking
Mm-hmm.
these questions. I know in like n-body simulations, they use splay trees to kind of group far apart points into like a single mass and
Yes.
incorporate that. But that bounds the number of interactions you have.
Yeah, I think there are two ways of handling this. The first is if you believe that the information from the nodes between unconnected, like long-range graph is enough, then you can build this long-range connections like here, what it's doing, right? Because you believe even with this random like point-to-point message passing, you'll be able to kind of aggregate information locally and pass information between the sets of point and sets of point. The other way is to define different level of graphs. So this is more really kind of a hierarchical graph learning realm, where you kind of have a one layer up, basically some substructure, like nodes that corresponds to substructures, and you try to build connection on those substructures. So each of them, I think, will be able to capture the long-range interactions, depending on how much of the kind of a group, the notion of group is important, or set of point is important in that case.
What about just like averaging the input signal from like all nodes outside of some k connections, like k edges away?
Averaging them, like treating all of them as a single node.
Is that all right to like incorporate long-range interactions, or do people have methods of doing this?
Yeah, as long as you know the geometry of that group, you're allowed to do it. Like for example, if you treat all of them as a rigid body group, then it's what we do in protein. Like we don't treat each single atom in the protein in our model. We actually treat each amino acid as a rigid group. So you only consider group-wise, translation notations. As long as you know this is a set of system that's rigid, you could operate them with the transformations that I mentioned here.
So I might have missed this, but for getting the graph, you're just using the point cloud, not the chemical bond information between the atoms?
Yes, this is where you're constructing a geometric graph.
Okay. Is there a reason the bond information isn't used?
I'm not saying like you're not using it. It's just in the geometric graph you're not using it. But if you're combining it with a normal graph neural networks, you can still message pass the bound information. But the bound information will just be kind of a scalar, it's a scalar information about the edge. So it is not it will not involve in this complex kind of equivariance and invariant transformations. And the answer is yes, you can always include more edge information and treat them as scalar. But the edge here, but the information passing that's defined here really just kind of try to say this is the group of points that you're passing information along, and you need to design the model to be equivariant when you do this aggregation.
Okay.
Yeah. I think there are also like ways of injecting like ordering information, like using the ordering information in, for example, protein sequences and define graphs based on that. Right. For the protein, one natural way is to include both k points that are most with biggest proximity to each node, as long as the neighborhood in the sequence space. Right, that's also what the AlphaFold did. So if you have 8 consecutive amino acids in like a long protein sequences, that 8 amino acid will also be included as the neighborhood to the node. Yeah. And then particularly, I want to mention this kind of boundary conditions. This is a special rule that you apply when you deal with, for example, crystal structures, like for a crystal with like a periodical, with periodicity in the space. Right, like some crystal or lattice. You could define these kind of small bounding box where when you construct the graph, you will be aware that this is kind of repeated unit. So I will only consider relationship within that bound and not between the boundaries. So that will slightly change your geometric graph as well. Yeah. So okay, but remember, this is not the reason that the equivariant deep learning or geometric deep learning is equivariant or invariant. It's just a way of constructing the input data. So you can connect it in any way, and your architecture still need to be equivariant and invariant. Cool. So geometric deep learning is actually a very deep and complicated field of studies. I assume like maybe most of you may not be going into the research in this realm, but just give you kind of a high-level picture of how complicated the landscape is becoming in the past few years. So basically, I think it all started with kind of the tensor field network, which is quite early work, but it's very powerful geometric deep learning that learns the equivariance using spherical tensors. Which I think in the next week the guest lecturer will talk about that architectures more. But basically, a lot of the effort spending in this field is trying to come up with different sets of unit operations that you can apply to the input feature, and basically how you represent your input features with different bases, such as when you apply this operation on these sets of bases, you will naturally get equivariance or invariance out of that, the message passing process. And there are particularly interestingly 2 ways of representing the bases. One is in the Cartesian space. It's kind of like the normal 3D space where we kind of define linear operations in the 3D space with this like matrix operations. And there's also kind of a spherical tensor space where you could use slightly different bases that's kind of defined in terms of like spherical harmonics, which characterize rotation better. And a lot of the complex equivariant architecture uses that spherical tensors. And more recently, there are proposals to try to come up with unconstrained GNNs that it's more, how to say it, it's able to kind of capture the equivariance and invariance in a more flexible way. And that could lead to maybe better generalization or expressiveness. But today, we're going to mostly focusing on the first line of work, which we call it invariant GNNs or invariant geometric deep learning architectures. And we'll go into why they can keep the invariance with these architecture designs. Yeah, and then again, like the applications can be very, very rich, from predictions to generative model to simulations. I'm not saying that it's doing much better than, like the numerical solvers, right? It's not doing necessarily better than the numerical solvers or
Yeah, I was wondering what the intuition behind the geometric GNN for the dynamic simulations was.
Mm-hmm.
How
it helps the dynamic simulations. Yeah, so considering the simulation being write out what forces are applied to each atoms and how the atom will move based on its current position, current velocity, and the force, right? So you can see that in the simulation process, the input is your current state. The current state can include physical, the coordinates, velocities, and forces. And you try to output the next stage where you have an updated state. This is kind of exactly corresponding to what a neural operator can do as well. So with the deep learning architectures, you could let it learn from the real world simulation knowledge, such that when you apply it, you could use the modern compute units that speed up a lot of these interactions. And a lot of time, what we observe is, so there are two ways you can apply it. The first is to speed up the simulation, because although we know, like I said, the numerical simulator, they're hyper optimized and they're deliberately designed to do very high accuracy simulation. So it's not going to beat those simulators, but it's going to be much cheaper than those simulators. For example, you can basically go much, much faster than what a accurate simulator can do with some bearable amount of approximation errors, right?
Do you still have ways of making hybrid models?
Yes,
some interpolation?
definitely. Yeah, definitely. I think that's definitely a very interesting domain where people either do this physics-informed neural operators or try to combine both steps. Like you could perhaps iterate between the steps or make some move with the deep, even though the deep operators, and try to do corrections with. A lot of these things can be combined and then similar to other domains that use machine learning as well. Yeah. All right, so, and I forgot to say, sometimes there's just no accurate information about the forces or the force field or actual forces that you like to characterize the systems, and what you observe is the outcome of kind of the nature simulation of the forces, and therefore you can use machine learning to kind of learn or infer the intermediate steps. If you simulate with the neural networks and try to backpropagate the simulation error. And that's also what kind of the neural operators and neural DE sometimes can learn. Even if you don't know, even if the system is a black box, you can still learn and simulate it in a way that respect some of these symmetry. All right, so to be more specific, right, if you map these methods in this kind of 3D or 2D landscapes, it's a lot of time about what kind of tensor you use. Is it a Cartesian space tensor or spherical tensor? And what kind of invariance or equivariance the architecture is able to carry. And particularly if you deal with the kind of L0 tensor, which is almost like a scalar thing, which is why it's kind of invariance. There's also different level of information that you can consider when you come up with this scalarization. So let me see if I have that plot here. So one thing I want to emphasize here is, maybe let me ask a question. Do you think geometric deep learning is more expressive or have higher capacity than normal deep learning? If you think it's yes, raise your hand. If you think it's no, raise your hand. Great. Yeah. So as I hinted earlier, geometric deep learning is not more expressive than a naive neural networks. Actually, the most naive deep learning architecture, for example, multi-layer perceptron, is the most expressive or high capacity universal approximator. But that's not a good thing. I talked about it very earlier in class, right? There's all possible functional space that you can converge into, and not all of them are necessarily to be considered when you learn a function, right? And particularly that's what inductive bias help us, where inductive bias help us to concentrate on the modes that are more likely to be the correct answer. And in this case, the more likely mode are the equivariant functions, which we know that we don't need to look into the outer space, visit outer space of the landscape. But So this means that we're restricting the possible families of models that we can characterize with the geometric information, geometric neural network. So it's not more expressive, and it's also not more powerful or high capacity, but it can learn faster, and that's what the inductive bias is helping us. And it also does not introduce a bias, because we know this bias already exists in the function that we try to learn. So it's actually characterizing this bias. But it does not mean that this method is easy. And it actually is not very easy to train. And there could be some numerical instabilities when we train these geometric neural networks that sometimes make it kind of a trade-off problem when you apply it, right? Sometimes it's a good option, sometimes it's not. And again, like there's also like a lot of trade-off that you need to consider into when you build these networks, right? So basically, this grid here tells us like what level of information we include when we build these architectures. And a lot of them do not differ in terms of the equivariance or invariance, but they differ in terms of their expressiveness of when modeling these systems. So you can consider basically equivariance, quantity property, and expressibility as kind of two a little bit orthogonal, orthogonal directions where you can make your model more invariant or equivariant to certain operations, but at the same time you can vary the expressiveness of your model. Like the dumbest model, I mean, a very naive solution of invariance model is always output a fixed scalar, right? Always guess 1 no matter what you put in. But that's not a very powerful model, right? So there could be a lot of different architectures that are invariant or equivariant, but the power of expressiveness is different. And that's what makes this model here different. And when you gain more expressiveness, of course, a lot of time the computation cost will also go up. So that's why we kind of also need to make a trade-off when you design these architectures. And a lot of our course, the next 2 classes will be talking about different examples in this grid and how they make use of the information through this message computation and message update stage to keep these equivariance while also try to keep the expressiveness. All right, so let's start with deep dive into the invariant geometric GNNs. So as said in the title or in the name itself, invariant geometric GNNs capture the invariance to translation rotation, sometimes rotation, most of the times translation rotations together, captures the invariance properties of these roto-translation groups applied to the input systems. And the key differences among these different architectures is basically how we come up with these invariant values, derive these invariant values from the geometric features, such that we try to preserve the invariance at the same time, also try to keep most of the information about the geometric attributes. It might be a little bit abstract at this level, but you can consider by the order of scalarization here means how many buddies you consider when you do scalarization, when you turn these geometric features into invariant features. I'll explain that in more detail next, for sure. Right? So very naive, very simple way that you can think of that you can come up with a scalarized feature of geometry is the distance. Right? If you look at the relative distance of every 2 points, right, however you translate or rotate your graph, the relative distance will not change. So the easiest way we could come up with is just instead of, it's just to use the relative distance to capture this invariance of geometric features, right? So when we look at these message computation layers, which takes the scalar information, the position information, and some vectors, what it does is I just use the scalar features, and I just take the coordinates, and I compute the relative distance between every pairs, and use that as the message, like as the features to my message. So however I compute this message and however I aggregate them, this information will not change regarding to like how I transform my system, right? So this is a natural, very simple way of coming up with invariance and equivariance. So it's not like that hard as you thought. However, so if you look at the kind of the layers in the invariant genomes, right? From right to the left is, the middle is kind of the architecture of the interaction layer, or the layer where you compute message and pass the message. So and right hand side is like how you compute the message from the geometric features, right? X here are the scalar features. Sorry about the change of notations, but X here are the scalar features, and R here are the vector features, or sorry, the coordinate features. And we don't consider vector features in invariant geometric neural networks because it's not able to handle equivariance, right? So we drop all the vector features, we keep the scalar features, and keep the positional, like the coordinate features, which are vector, but they just used to keep track of their geometric information, and we throw away the vector features because the model lose track of equivariance. It's only an invariant model. And you can see that how they featureize these coordinates is to compute the relative distance of the two, and you can also apply kernels on top of these features, right? You could basically, the kernel is just some like transformation of the features, so it's not just like 1, 2, 3, 4, or just like a distance. So you can basically consider this as like adding expressive power to your models, right? And you could also apply, dense layers like MLPs or any kind of non-linearity on top of these features, as long as these features themselves are invariant. Like this whole operation is invariant. And after you compute this information, you will combine it with the scalar features. Here it just uses multiplication. You can also use addition. Like it doesn't matter. It does not change anything about the invariance. And you put it back to the message passing layers here. You can see that, again, like we apply this atom-wise computation because, again, this is a geometric deep learning, but it's also a graph neural networks. So we also want to keep the permutation invariance. And this part is exactly like how we handle permutation invariance in GNN, right? We just look at each single node, we apply node-wise changes, and we aggregate information in this step. And in the final layer is just you basically turn this embedding into mapping them with some aggregations. Again, it could be like a sum or average, any pooling layer that is invariant, that is permutation invariant. You then get a final output. So it looks kind of similar to graph neural networks, except for how you handle these features, particularly like the coordinate features here. But it does. Now that we handle invariance easily, right? Is it a powerful architecture, or is it expressive enough? Actually not. So you're losing a lot of expressibility even with the gain of these invariants, because if you look at maybe the two examples, right? The A is two sets of big different object, and you can see that basically, like if you swap the distance between some pairs, right, you still get the same sets of pairwise distances, but they're actually different graphs. They're actually different geometric graphs. You cannot, you shouldn't be treating them as like same to each other. And second one is also another good demonstration where you can consider that the only change between these two graphs is this blue point being kind of mapped. You kind of applied some reflection on this with respect to this this axial here, and the blue point now goes to the bottom part of this this subspace. And if you compute the pairwise like distances, it's going to be the same sets of distances, but these two graphs are very different. You cannot make they're not the same graph, basically. So how to say that? Like, for example, if you consider like applying like rotations or translations to the second graph, right? It doesn't become the first graph, but their features are the same because within each of the graph, no matter how you transform it, these features remain the same. So it's invariance to each of the system, but these two systems are fundamentally different. So if we use the ShrewNet, we're not able to tell apart the difference between these two, and we'll be getting similar predictions with this network. So how can we handle this better, right? So an extension is, instead of considering this like pairwise distances, now we involve three-body, and we kind of consider like a three-body scalarization, where instead of just computing the pair, we add a third point, where the third point is kind of the two hop neighbors of the point that we're considering, right? And so for all triplets of points, we now take their pairwise distance, but at the same time also look at this additional angle information among the current point, the point that we look for distances, and the third points that connect to the second point. So this is, again, a invariant operation, like invariant scalarization, right? If you kind of, I mean, actually, basically, the more buddy you consider, like the whole system, when you change the whole system together, like these two entities does not change at all, right? Because this is a rigid, if we're applying changes to the system, we know that it does not change relative distance, and if you rotate the 3 points, right, together, it doesn't change the angle at all. So, so now that we compute every 3-buddy order of scalarizations, we'll be able to tell the difference between this point and this point, because their angle is different with respect to the red point, right? So with this kind of additional buddy that we take into consideration in the scalarization, basically the buddy order of scalarization is defined by the number of nodes that are involved when we compute this local invariant scalars. So, so here we have 3 buddies, so the order is 3. So you can see that the difference here is when you compute this message, right? You consider the distance between I and j, and at the same time you kind of compute the distance between jk and their angle as one quantity here. And if you look at the DimeNet, which is basically, you can see the model takes in this triplet featurization where you have the distance, and again, you can apply kernels, right? And then you have this angle information. You can, again, apply some kernels, which we don't go into details, but this kernel is able to map distance and rotations. And it's, yeah, everything else is very similar to what we see previously, where you have these interaction layers. Again, it's kind of doing, message computation and message passing within this interaction. But as long as we know that our add features contains these local scalars that derived from the 3 buddies, we make sure that the output of the network is invariant to translation rotations. So with this information, we'll be able to kind of tell apart this kind of graphs. But this is not still enough, right? You can still come up with 2 sets of different molecule graphs or geometric graphs with exact same number of unordered sets of distances and angles. And this is another example, because you have this kind of additional, still you have this kind of a rotation that we need to handle, the freedom of this rotation, where you could have like 2 very different molecules, but the only difference is that it cannot be captured by this 3-buddy scalarization. So if we go one more buddy, basically, if we look at every kind of quadruples, or like 4 buddies, then now we have more, again, a little bit more information that restrict kind of captures all the degree of freedom that you can observe in this system, right? So if you look at this 4 point here, right? One thing you can do is you can rotate the edges. You can rotate these 2 points along k. So this is you can consider this is the picture if you look at the 4 point from this angle, right? But if you look at from the other side, there's another angle here that we call it torsion angle. It basically say like for this 4 point, you can basically rotate L and I with respect to kind of fixing the ij edge as kind of the axle, and you rotate these 2 points along this axle, right? You can see that the 3-buddy information does not change, right, between ijk and ljk. But this angle that we're capturing here is the additional degree of freedom, which we call torsion angles. So previously, if we use the DimeNet, we would not be able to tell the difference between this and this, right? But these are 2 different graphs. But now that we add this additional torsion angle, if you look at from this angle, this is basically the torsion angle that's captured here. it kind of constrained that additional degree of freedom now that we can tell apart the difference between this and this. So, so GemNet is going one step further. It characterizes every four bodies, groups of four bodies in the atomics in the point cloud, and featureize both distances and angles and the torsion angles for the four bodies. So theoretically, there are analyses saying that GemNet, like if you consider every four bodies, then it is kind of theoretically universal that like any possible 3D graphs, you could tell the difference with these operations, but it's still not perfect. Like again, like in this theoretical analysis of universality or expressibilities, it assumes a complete graph. So instead of look at local graph, you need to consider all pairs of nodes being continued and a certain discretization to really prove the universality. And also, like, this computation is not trivial at all. Like, for every four body, you could enumerate every four bodies and compute these angles. It requires a lot of computational cost. So sometimes you just don't need this level of expressiveness when we build models. And a lot of time, like even just telling apart, this information or just the pairwise information already carries a lot of the information we need. And that's actually the ShoeNet, despite of its simplicity, is actually a very popular architecture. So to recap, to summarize, like these invariant GNNs, they preserve this invariance by pre-computing this local scalarization from the geometric information, particularly the coordinate information. Which can be a good thing or a bad thing, because the good thing is once you pre-compute the scalars, you can do any operations on top of them, right? You can combine them, multiply them, or add, subtract, or nonlinearity. Like you can apply any operation on them and preserves the invariance. And it also considers this high-order interaction if you do this kind of four-body thing. But it's also very expensive. Basically, like you lose kind of the flexibility of what feature you want to use and like what level of information you want to consider, because you need to make a decision before like feed them into the network, like what information I will lose track of. So that makes this architecture powerful, but at the same time it can be expensive and less flexible. And one apparent drawback is that it's not able to capture the equivariance. So just through this scalarization, we cannot guarantee we can make prediction of vectors that are equivariant to input. So that's also a drawback of this kind of models. So there's alternative thoughts of making just like equivariant functions with the neural networks, such as you don't need to pre-compute this scalarization, you just need to feed the raw geometric information. And through this operation of equivariance, you're always carrying this invariance in this equivariant transformation. So at the end, at any time, you can still derive this invariance from the equivariance transformed embeddings. And that's what we're going to talk about next time, which are the line of work that does this equivariant neural networks. But before that, as I mentioned, the invariant architectures are very simple, and it's already very powerful tools for a lot of the applications. And one such successful application is called protein MPNN, which is used to solve the inverse folding problem of the protein. It sounds a little bit strange to talk about inverse folding before we talk about folding, but you already know like the folding process is like, as I said earlier in the central dogma, like all of these downstream functions are actually determined by the initial like information carried in our gene, and that specifically means the sequence information, right? So when we design a protein, we can of course predict the functions by taking into structure information, but what we're designing essentially is the sequence, because that's the only thing we can manufacture. We cannot directly manufacture a structure without going to the sequence. So if we consider the actual problem of drug design, right, the problem is to find the sequence that gives us the function or structure that we want. And a lot of time, structure is easier to design because we kind of know like what landscape or shape complementary we want. But so sometimes there's some pipelines that you come up with the structure first, and then you want to go back manufacturing these structures, and then you have the question of here is like what sequence I should use to make this structure. So this is one way of using sequence design or inverse folding. Right? So the problem of inverse folding is defined as the problem to find the amino acid sequences that will result in the desired protein structure, which is the inverse process of the folding operation, which folds an unstructured random like peptides into a 3D conformation. And a lot of time what we look for in this inverse folding process is also finding a protein sequence that is more desirable. What I mean by desirable is you can come up with certain properties, like I mentioned earlier in the protein function prediction, right? Particularly stability, thermal stabilities, expressibilities, right? And also sometimes solubility. If I want to find a sequence that gives me this structure, it would be great if my sequence also have these nice properties of like being stable and like functional. Although sometimes you can have multiple sequences that map to similar structures, they do not have similar kind of stability and functionality. That's why like in the nature you don't observe like all possible sequences, even though they could lead to very similar structures. So you can think of the problem of inverse folding being this first step here, where you have some notion of structure already, and you kind of try to guess the sequence, or you have a sequence structure pair to start with, but you want to change the sequence, or we call redesign the sequence that preserves similar structures, but may lead to optimize the sequence that is better than what you already observed in the starting design. So these two steps, both of them involves this inverse folding process. And after we get a sequence, we can definitely like put this into E. coli and we express them, and we can measure like their actual properties with experimental verifications. So this is also why we need the sequence. No sequence, no protein. Cool. So the protein MPNN is a seminal work that just came out like 2 or 3 years ago during the pandemic, from the Baker Lab, who just won the Nobel Prize, where it's kind of this tool was built with the actual need from protein design, right? In their lab, the Baker Lab has always been spending effort in computationally model the structures of the proteins, right? With either generative model like diffusion or earlier like sets of like Rosetta fold or Rosetta toolkits, they try to come up with templates or assemble templates in a way that form the kind of the preferred geometry or shape that they like. But when they actually made the protein, you actually need to figure out what sequence to put into those templates, that at the end you will be able to like actually make something that folded into structure you want. So previously they're doing this with kind of what they call hallucination, where if you have like a folding prediction like AlphaFold or Rosetta fold, you basically have a function mapping between X and Y. Y is your structure, right? And then you can consider one way of making X or changing X to give you certain Y is to directly inverting this process. For example, through adversarially attack your Y here, right? And if you just maximize the likelihood of observing Y from this predicted model, you can get some gradients with respect to X, right? Or if you perturb your X, you can observe the predicted likelihood of this X being the structure you want. So with this hallucination, they call it hallucination. A little bit weird because we know that it's a bad thing in computer vision or natural language, but in protein design, there is a line of work called like hallucination, where they use it in a positive tone, basically as a tool of figuring out, traversing the sequence space, such that you will get a good sequence that if you use AlphaFold to predict it, it will give you what you want. So you're kind of adversarially attacking the AlphaFold prediction by changing your sequence. And this is what is previously being done for this inverse folding task, and they found this to be very useful already. But after this boom of like geometric deep learning, then naturally we have the thoughts like, why not just directly learn this because we have the data, and we should be able to learn it from the data that we use to predict folding. We just swap the input and output and train a different model, right? So that's the intuition of the motivation of building this MPNN. And like a lot of time, if you train for something, you perform better than something that's not trained for it, like in the end-to-end fashion. And that's what we observe. That's what they got actually by building a model using invariant geometric deep learning. They're actually getting improved the result comparing to like hallucination and other methods. But so what this PrediMPN does is like it involves two parts. Both of them are graph neural networks, geometric graph neural networks. The first part is the structure encoder, where it uses 3 layers of invariant MPNN, which basically kind of like the ShoeNet we talked about previously. That basically directly taking the pairwise absolute distance and apply invariant message passing to get an encoding of the structure without information. And then during decoder, the decoding stage, they autoregressively. So at this stage, you can treat like every node has. You can think of this geometric graph has each of node is associated with a type of scalar feature, which is the type of the amino acid, which is a one-hot feature, and this is a scalar feature. At the beginning, it is a mask. Basically, all the positions are treated as mask. And during the decoder stage, it again applies some message passing over a new graph, where in this graph, part of the node has assigned identity of amino acid, and part of them is still masked. So by dynamically changing these node features and redo this message propagation, it is able to come up with kind of like an autoregressive model that, like, condition on the current partially decoded graph, we can make a prediction of the next the atom type, the amino acid type for the next amino acid in the graph. So how this is done is by adding this causal mask to the decoder, where in the decoder stage, part of them only sees this masked embedding of the node, and part of the graph actually sees the structure, the sequence information, and therefore have a slightly different embedding. It's kind of like the causal mask in transformer as well, just that the transformer now becomes a geometric MPNN. So just to recap, we will talk about the structure in more details later, but just in a high level, each amino acid is this small unit of we'll call it amino acid, which usually comprise in the backbone several atoms. So maybe it's easier to look at 3D space. So this is the side chain of each amino acid, and as we talked about before, each amino acid must have a carbon in the middle, which we call it C alpha or alpha carbon, and the C alpha is directly connected with the amino group, which is the NH2, and the carbon oxide group, which is the CO here, which is C and OH here. So through these reactions, these two groups will be connected with the correct enzyme, and the water will come out, and the next unit will be connected where the carboxyl group of the next amino acid will be connected to the previous amino group. So you can get, so that's how we get a polymer from a repeated unit of the single amino acid. And this is kind of like an example of two connected amino acid in a chain, or in the kind of a bees in a stream, where we call this connected stream of atom comprising the nitrogen, carbon alpha, carbon and oxygen from the carboxyl group. The repeated chain of these 4 atoms, the backbone of the protein, because this is what actually get connected together and form the kind of the longest chain in the graph of a protein. And then these CB or beta, carbon beta is what's kind of used in this side chain, which kind of like these kind of small side chains on the 2 sides of the main skeleton or the backbone of the protein. So again, the protein has can be characterized by the backbone information, which is where this NC alpha CO is located in the space, and you can easily define in order the chain. If you thread these atoms up, this will be the backbone of the protein, and they also have these side chains, right? Sometimes it's hydrogen or or some functional group that includes this carbon beta. But this side chain will stop because it's just kind of a small, like really short and small chain that's kind of dragged out from the main chain, which is the backbone. So when we talk about the backbone or with structures, a lot of time you can consider it means actually the geometric information of the backbone atoms, which is the NC alpha, C, and O. There's like 4 atoms, because these 4 atoms the position of this 4 atom uniquely determine the geometry of your backbone already, and that's what a lot of time when we talk about structure information or 3D information for proteins, it could refer to this simplified version where we don't keep track of all the atoms in amino acid because it's too expensive and unnecessary, and we only keep track of information about these 4 atoms. In addition, this side chain is basically definitely out of the backbone, right? So it can also have like this torsion angle where you could basically rotate this along this C alpha, this side chain groups, right? So if you want to capture that side chain information, in addition, try to capture like the C beta, where the C beta is located. That will kind of give you a little bit of information about where the side chain is located as well. So that's exactly what's used in protein MPNN, where you can consider like a chain means kind of the connected string of amino acid, or the beads in the thread. So when we assemble like proteins, some of the bigger proteins, they can comprise multiple chains. Basically, you have 2 different threads of amino acid or 2 peptides, and they each fold into subunit, and they can be assembled together. But these 2 chains are not interconnected through the same kind of chemical bond within the same chain. Or if you consider like interaction between 2 proteins, right? These are also like 2 separate chains, but they're kind of interacting with each other. So MPNN is able to handle this by like modeling each separate chain separately. Basically what it does is you can see that this is definitely a distance-based invariant GNN like SHUNET, right? So what it does is try to characterize the pairwise distances between C alpha and C alpha, which is C alpha of 2 residues. And it look at the neighborhood of each amino acid, and it takes, I believe, the closest 24 amino acid as the neighborhood defined in the 3D space. And sometimes it also captures these primary sequence information by injecting these information as a positional encoding into the node. So it gets, as an input, scalar features, which are positional encodings, and the atom type information, which is the mask at the beginning. And they get geometric vectors, which is the relative distance between pairwise pairs of the points. And there are 2 versions of MPNN. One is to only compute distance between C alpha and C alpha. That's like C alpha only MPNN. And they have a different version that actually captures all pairwise distances between C and C alpha CO in like 2 consecutive, not 2 consecutive, but between pairs of amino acid. And that distances becomes the features of the edge that we use to characterize this invariance. Basically, these are kind of the local features that we compute as the input feature. And again, they're using these RBF kernels, which is just kind of a featurization on top of the raw distances. In the encoder part, the encoder part is exactly what we talked about in the SHUNET. Basically, you encode these distances, and this becomes the geometric information you put on the edge.